Hello my fellow people. In the next few videos, we're going to be talking about case control studies, cohort studies, and measures of association, namely odds ratio, risk ratio, and hazard ratios. And to do this, I'm going to start with the big picture by talking about the different types of epidemiologic studies and statistics, and then narrow down on our topics of interest. Now let's start with a brief overview of epidemiologic studies and applied statistics. Epidemiologic studies include descriptive studies and analytical studies. Descriptive in this context implies that there is no control or comparison group. All descriptive studies are, by definition, observational studies, in that they do not involve an intervention. Descriptive studies include case reports, case series, cross-sectional studies, and ecological studies. Although they are pretty low on the hierarchy of evidence, case reports and case series are generally where new discoveries begin. Case reports, for example, bring attention to rare and peculiar clinical findings, while case series can detect the presence of a pattern and be used to generate new hypotheses or be the first to describe new, undiscovered disease processes or medication reactions. Cross-sectional studies involve observing or comparing individuals in a population at a single point in time. Because there's only one time point, no temporal association, like exposure and outcome, can be made. Also, unless the rates of exposure and non-exposure are constant over time, an exposed and a non-exposed group cannot reliably be constructed for comparison. Ecological studies pool population data, usually from other studies, to compare exposures and outcomes among populations. Because they compare populations, not individuals, they are not able to control for behaviors or demographics of the groups they study. This makes them very susceptible to confounding bias and effect modification. In fact, the term ecological fallacy is used to describe the erroneous conclusions that can be made when statistical data about a population as a whole is used to make inferences about the behavior of its individuals. And this is at least in part due to confounding and effect modification. This is why ecological studies are descriptive studies and not analytic, and why they can suggest associations but cannot prove them. Analytical studies include observational studies and experimental studies, and are carried out with the intention of testing hypotheses. The analytical type of observational studies include case control and cohort studies and some cross-sectional studies. Similar to descriptive studies, these studies do not involve an intervention. However, unlike descriptive studies, these studies by design possess a comparison group and are carried out with the intent of elucidating an association between an exposure and an outcome. Keep in mind that these studies may be used to discover or verify association, but they cannot be used to support the claim of causation. Case control studies involve separating subjects into two groups: those with a disease or outcome of interest, the cases, and those without, the controls, and then comparing their history of exposure. Cohort studies involve separating subjects into exposed and non-exposed groups and then following them over time to compare the development of a particular outcome, such as a disease or a disease complication. More on these two in a minute. Now, cross-sectional studies can be considered analytical. If the rates of exposure within a population under study remain relatively constant over time, an exposed and a non-exposed group can be constructed. The non-exposed group serves as a comparison group, thus making this study an analytic study. However, these cross-sectional studies are different from cohort studies, since exposed and non-exposed groups are not defined at the outset and are not followed over time. Rather, exposure and disease prevalence data is collected at the same time and then used for comparison between the two groups. For example, making a comparison between the proportion of exposed persons with disease to the proportion of non-exposed persons with disease. The other category of analytical studies is the experimental studies, which mainly includes clinical trials, such as randomized control trials, non-randomized control trials, crossover studies, and non-inferiority trials, but also community trials. The word experimental implies the manipulation of an independent variable to measure its effect on a dependent variable. In this context, that independent variable is the intervention. Unlike observational studies, clinical trials involve an intervention and can demonstrate a cause and effect relationship, not just a mere association. However, proving causation requires more than a single well-executed randomized control trial. To be more specific, a cause and effect relationship is established with the help and guidance of the Bradford-Hill criteria, which, in Sir Bradford Hill's own words, are more aspects of association that demonstrate causality rather than strict requirements or rigid criteria. Although the precise definition, weighted importance, and methods associated with each criterion has changed since their introduction by Sir Bradford Hill in 1965, they still remain an important set of guidelines to aid researchers in establishing causal relationships. For example, Criteria 1 was initially put forth as the greater the association, the more likely there is a causal relationship. However, nowadays, we put a lot more stock into statistical significance of an association rather than the magnitude. Another criteria, consistency, is upheld when multiple studies and trials carried out using different locations, study groups, and methods show a consistent association between two variables. The consistency criteria is still regarded as an important criteria, although nowadays consistency is sought not just among epidemiologic studies, but between epidemiologic studies in other fields like molecular biology, pharmacology, and bioinformatics, in what's known as data integration. This is all summarized very beautifully in an article by Kristen Fedak for those who are interested. As stated earlier, cohort studies compare rates of outcome between exposed and non-exposed groups, while case control studies compare rates of exposure between cases and controls. For both studies, the goal is to determine if an association exists between an exposure and an outcome. And in both types of studies, two groups are constructed with the aim of having participants similar in every way except for our variable of interest. This allows us to minimize the effect that confounding variables and effect modifiers might have on the association being studied, and by doing this, we help ensure the internal validity of our study. So for cohort studies, we start with our exposed and non-exposed group, and then follow them forward in time to see if the disease or outcome of interest develops equally in both groups, indicating no association, or if it develops more frequently in one group than another, indicating an association. Cohort studies can be done retrospectively, where we start at a point in the past and work toward the present, or prospectively, where we start in the present or recent past and work toward the future. The important thing that really differentiates cohort studies from case control studies is that in cohort studies, exposed and non-exposed status is established at the outset, and patients are followed forward in time. The results of cohort studies can be reported as odds ratio or risk ratio, or some other measure of risk, as we'll see in a bit. And the question that we are trying to answer with cohort studies is this: what is the probability that a person with a particular exposure will develop the outcome of interest? Now, for case control studies, we start by identifying our cases and controls at the outset, and then, looking backward in time, measure and compare rates of exposure in and between the groups under study. And this comparison is done with the intention of seeing if an outcome and an exposure have a significant association. To be more precise, case control studies investigate whether having a particular outcome is associated with increased odds of having had a particular exposure. If both cases and controls have equal rates of exposure, then we say that no association exists between outcome and exposure. If exposure rates between cases and controls are not equal, an association is said to exist. By study design, case control studies are always retrospective, and although they are generally easier to conduct than cohort studies, case control studies are notoriously susceptible to recall bias and survivorship bias. Recall bias occurs when a person's outcome influences their recollection of a past exposure, and survivorship bias occurs when subjects who did not survive long enough, possibly due to a more severe or progressive disease subtype, are not included in the study. The question that case control studies try to address is this: what are the odds that a person with a particular outcome was exposed to a particular exposure? It's important to point out that we cannot turn this around. We cannot deduce from a case control study what proportion of persons with a particular exposure will go on to develop the outcome. Also, as we'll see in a bit, because case control studies do not measure the incidence of disease development among a group of exposed individuals, they cannot be used to generate measures of risk, and so their results can only be reported in odds ratio. So we've established that cohort studies and case control studies are used to find association. But how can we determine if an association we measured in our study is not just a result of chance or random sampling? Well, to do that, we will need to use statistics. There are two main categories of applied statistics: descriptive and inferential. Descriptive statistics are used to summarize data collected from a sample using measures of central tendency, dispersion, and distribution, all of which are a type of statistic, while inferential statistics uses sample data distilled and summarized with descriptive statistics to make inferences about a population or a population parameter. The fancy way of saying this is that we use inferential statistics to infer the parameter of a population by using the statistic of a given sample. In this context, a statistic is a numerical summary of a sample, such as a sample mean or a sample standard deviation, while a parameter is a numerical characteristic of a population, such as a population mean or a population standard deviation. So as an example, the mean or average height and range of heights of adults who frequented a local grocery store last Tuesday are examples of a statistic, while the mean or average height of all U.S. adults and the ranges of heights are examples of a parameter. Taken by themselves, descriptive statistics cannot be applied to a broader population. To do that, we need the help of inferential statistics. It can be said that there are two main objectives when it comes to inferential statistics: test our hypotheses and estimate population parameters. Hypothesis testing involves using statistical tests to see if our results are statistically significant. And it can be done using a variety of methods depending on how the study is designed, the sample number, and whether the variables are ordinal, interval, continuous, or categorical. Estimation of parameters is an attempt to use sample data to predict or estimate the population parameter. This is done with point estimates, which can be a mean, a measure of association, a measure of occurrence, or a regression coefficient. We can then use point estimates and standard error to construct interval estimates, most notably a confidence interval. In this video, we will be focusing on p-value, confidence interval, and measures of association. But keep in mind, both types of epidemiologic studies rely on both types of statistics. For example, a cross-sectional study will use a population sample to generate a mean with a standard deviation and will also have a confidence interval reflecting how well it can approximate the true population mean. And for a randomized control trial, a mean value with a standard deviation will be generated using descriptive statistics, and then inferential statistics procedures will be used to generate a p-value and/or confidence interval which can communicate statistical significance. Understanding p-values and confidence intervals is vital for appraising the significance of epidemiologic studies, and also for doing good on board exams. As mentioned earlier, they can both be used to communicate whether or not the findings of a study are statistically significant. But what exactly are they and how do we interpret them? The p-value, or probability value, reflects how likely it is that the results of a study were obtained by chance, or how likely it is that the null hypothesis is correct. More specifically, the p-value is equal to the probability of obtaining the acquired result, or one more extreme, at random. Almost each and every possible study result has an associated p-value that is determined by calculating a test statistic using a statistical test. For example, the t-test, a statistical test, compares the means of two groups by generating a t-value, which is a test statistic. This t-value can then be used to calculate a p-value. Once calculated, the p-value is compared to a preset significance level, labeled alpha, to determine if there is a statistical significance. If the p-value associated with the acquired result is less than or equal to the significance level, then the null hypothesis is rejected and the study result is deemed statistically significant. In the example on the right, a standard normal distribution curve is depicted with the x-axis representing all possible results for a study and the y-axis representing how likely a particular result is to occur, assuming the null hypothesis is correct. The total area under the curve, and really under any standard normal distribution curve, is equal to 1, which makes sense because there's a 100% chance of obtaining any one of all possible results. The distribution plot is centered around the null hypothesis mean, which happens to be the point of greatest probability density. And this makes sense too, since the most likely result of a study, if the null hypothesis is correct, will be the null hypothesis mean. In this distribution plot, our observed result is marked in purple, with a blue shaded area equal to its corresponding p-value. In this case, the p-value is 0.07 and our significance level was set to 0.05. And the way we can translate this into English is by stating that the probability of obtaining our result, or one more extreme, completely by chance is 7%. Now we set our significance level at 0.05. meaning we are only willing to accept a 5% probability that the result was obtained by chance and not due to the independent variable. Because the p-value associated with our observed result is greater than the chosen significance level alpha, we cannot reject the null hypothesis, and so our result is not statistically significant. Okay, now let's talk about confidence intervals. Many students think of confidence intervals as the range of values within which the true population mean is likely to exist with, say, a 95% probability. And although that's not exactly true, it's usually close enough for most board exams. Conceptually, the confidence interval is an attempt to estimate the range where the true population parameter exists with a certain degree of confidence. The key word here is confidence and not probability. And this is because the true population mean, although unknown to us, already exists. And so there's a 100% probability that it is what it is. This is analogous to the fact that a baby born yesterday has either a 100% or 0% probability of being a boy. But without actually knowing the sex, we can only state that we are 50% confident the baby is a boy. The confidence interval is derived from two statistical ideas, the law of large numbers and the central limit theorem. The law of large numbers implies that the larger the sample size, the closer the sample statistic will be to the population parameter. And the central limit theorem states that, assuming a sufficiently large sample size, the data will be distributed in the shape of a bell curve. So to get a bit more technical, just for a second, a confidence interval represents the range of values whose distance from the sample mean is not statistically significant with respect to the chosen significance level alpha. And the confidence level communicates how likely it is that the confidence interval estimates the true population parameter. Typically, the confidence level is set at 0.95, meaning a significance level alpha of 0.05. So a 95% confidence interval is the range of values around our calculated sample mean where 95% of subsequent sample means are likely to fall, assuming a constant margin of error. For example, if we conducted the same study another 100 times, then the interval range of our initial 95% confidence interval would be expected to include the mean outcomes of 95 of those studies. Okay, let's get out of the weeds now. Simply stated, confidence intervals are very useful pieces of information because they allow us to represent both statistical significance and the magnitude of effect, which allows us to estimate clinical significance. At a most fundamental level, confidence intervals are created using a point estimate and a margin of error. Below are two examples of equations we use to calculate confidence intervals. The top one applies to the confidence interval associated with the mean, while the one below is for risk ratio. Although we will not be using these equations for any calculations in this video, I just want to point out how the confidence interval mainly depends on three things: our desired confidence level, the sample size, and the sample standard deviation. Notice that there's an inverse relationship between confidence interval and sample number, meaning that with greater sample size, the confidence interval becomes narrower. Also, notice how confidence interval is related to standard deviation, such that a smaller standard deviation can produce a narrower confidence interval, while a larger standard deviation can produce a wider confidence interval. When it comes to determining significance, it is important to ensure that the confidence interval excludes the null hypothesis. For example, if the null hypothesis is that no difference exists between study group and control group, then in order to reject the null hypothesis, there must be no overlap between the control and study group confidence intervals. In the graphic below, we can see that the intervals do not overlap, and so we can say that a statistically significant difference exists between them. Moving them closer together, we see that even though there is some overlap with the distribution, overlap of the 99% confidence interval, for example, the 95% confidence intervals do not overlap. And so assuming a significance level of 0.05, we can still call this statistically significant. But if there's an overlap of the 95% confidence intervals, then we interpret that there's a greater than 5% probability that the difference between the control group and the group under study was due to chance, and then conclude that there's not a statistically significant difference between the groups. The key takeaway here is that confidence intervals depend on three main factors: sample size, dispersion of the data, and confidence level. Both the size of the confidence interval and the magnitude of effect play a role in determining the statistical significance. If the sample is large and the standard deviation is small, the confidence interval will be narrow and significant overlap is less likely. But if the magnitude of effect is small, the confidence intervals will be closer together and more likely to overlap, resulting in a non-statistically significant result. This is why the expected magnitude of effect size is used by investigators to figure out how big their sample needs to be. Now, equally as important as understanding statistics is understanding the limitations of statistics. P-values and confidence intervals are very useful tools. However, at the end of the day, they are simply mathematical procedures that generate numbers based on assumptions of ideal circumstances. To truly appraise the validity of a study, we also need to look at the study design, sampling methods, the methods of data collection and data analysis, and the conclusions that authors are attempting to make. And then be mindful of the fact that statistically significant results do not necessarily translate into valid conclusions.